Well, since it's been a while, we've been on a sort of a extended spring break. Let's review a few things that we covered right before the break, and we'll launch in from there. And we'll look over again this quantum mechanical scattering from delta function potential. Uh, all of this, of course, is in one dimension, and our potential in this case, I'm going to locate the position of this delta re, repulsive potential at the origin. So essentially, that's assuming that our potential energy for the particle mass m is v naught, where v naught is some positive constant times a delta function that's located right at the origin. So here symbolically, the v naught is a constant that in some sense measures the strength of the interaction. And we'll have more to say about that a little bit later. Classically, that problem is pretty simple. Yeah. If we fire in from minus infinity a particle of mass m and give it finite amount of energy E, then the potential energy is zero everywhere on this side. And as a result, the particle never has enough energy to get over this infinite potential energy barrier at the origin. And the particle is just going to come in and bounce off of it and come back. So classically, the infinite barrier here, potential barrier, is prohibitive, and that it never lets any of the particle get any particle that's incident there over into this region x greater than zero, and that's said to be a classically forbidden region. And the reason is we can't, any physical particle, we can't give infinite energy, so it never has enough energy to get over this infinite barrier. Quantum mechanically, the problem is kind of surprisingly different. Yeah? And as usual in quantum mechanics, we have to solve this time-independent Schrodinger equation for the given potential. In this case, the v of x is b naught times the Dirac delta function potential. And like we've done before, we separate it into two easy regions, namely x less than 0 and x greater than 0. For x less than 0, the potential is 0 everywhere for x less than 0. And the above equation reduces to a very simple one that we've solved before. We do it exactly the same way as we've done before. Again, I'm assuming I've launched a particle m in with an energy E, and pull everything, all the constants, over to the right hand side. 2me h bar squared, those are all positive constants. So I simply lump those together into a k squared, use k squared to indicate I have knowledge that that's positive. And then rewrite the equation in sort of the standard form that you would see in a ordinary differential equations course. And as we know, this has the general solution. Psi is equal to a integration constant times e to the I kx plus b e to the minus I kx. A and b are both general integration constants. So that's for x less than 0. For x greater than 0, it's essentially the same problem. For x greater than 0, strictly greater than 0, the potential is 0 again because the delta function vanishes there. And as a result, the equation becomes exactly the same, and we can solve it in this region x greater than 0 and get the general solution in that region, which is psi is equal to c e to the I kx plus d e to the minus I kx. Our general solution then, which we have virtually everywhere except exactly at x equal to 0, has got four constants to be determined in it, a, b, c, and d. And it's of this form for x less than 0 and of this form for x greater than 0. Graphically, we have this situation. We have an incident beam, or incident particle, which is the e to the I kx term. We get a reflection, which I'll call psi reflected, which is the b e to the minus ikx term. Transmitted, we get a c e to the ikx. And then in general, you also get on the right-hand side the possibility of simultaneously being firing in particles from positive infinity. So the most general solution, we're simultaneously firing in particles from the left and a particle of mass m from positive infinity from the right. But we're only looking at the case where we're setting up an experiment and we want to describe the experiment where we're firing it in only from the left. And so we'll set d equal to 0 to represent that case. And then we have our sort of standard form. The delta function, the incident wave function, the reflected, and the transmitted. And now our general solution looks like this. And of course we've got the k. The k is the same on both sides, and that's just 2m, the incident energy of the particle over h bar squared. Well, the next thing we would generally do is apply boundary conditions, and the easiest one to do, and I'll do that at this stage, is to apply the condition at x equal to 0. As we know, one of the conditions for the wave function is that it has to be continuous and have continuous second partials for the most part. We'll relax that second constraint a little later like we've done before. But for it to be continuous, then I have to have psi as x approaches 0 from the left equal psi, the wave function, as x approaches 0 from the right. On the left side, I've got the solution a e to the ikx plus b e to the minus ikx, and I have to evaluate that at x equal to 0. And then on the right side, it's just c e to the ikx for the transmitted wave, and I have to evaluate that as 0. And that leads us to when I plug in 0 for all of these x e to the I plus or minus kx's, they all become 1. And so this equation reduces to just a plus b is equal to c. So continuity of the wave function requires the wave function to be of this form here. Still some indeterminacy. I need to determine the amplitude A, B, and C in this case. But now I can put in the equal signs because this solution with A plus B equal to C is continuous at x equal to 0.